Okay, today I will show you the Laplace transform. Uh, it is left actually because I have already shown you the Fourier series and Fourier transform. So only Laplace transform is left. So let's discuss about the Laplace transform. This sheet has been taken from the Illinois Institute of Technology. It is an American university. Okay, so Laplace transform. So let f be a function. If f it is a function, then its Laplace transform is denoted by the corresponding capital letter F. So another notation is this, like this. You can write the Laplace transform. Input to the given function f is denoted by t. Input to its Laplace transform f is denoted by s. By default, the domain of the function, this is the domain, is the set of all non-negative real numbers. The domain of its Laplace transform depends on f and can vary from a function to a function. Okay, so definition of the Laplace transform. The Laplace transform f is equal to fs of a function is defined by like this way we can define the Laplace transform. Laplace transform of f in the frequency domain or s domain can be written as like this: 0 to infinity, integration of 0 to infinity e to the power minus ts f of t dt. The integral is evaluated with respect to t, that means that dt. Hence, once the limits are substituted, what is left are in terms of s. So if we omit the limit, then we will get the output in the s domain. Example, find the Laplace transform of the constant function. So the question is to find the Laplace transform of this function. So f of t is equal to 1, where the range of t is 0 to infinity. So Laplace transform, what would be the Laplace transform? Like this: 0 to infinity, e to the power minus ts ft dt. So instead of ft, we can write the 1. So see here, what would happen? So we can write limit b tends to infinity. So integration of, let's say instead of infinity, you can write the b. Okay, positive infinity. So 0 to b. So integration of e to the power minus ts would be e to the power minus ts divided by minus s. Okay, s is not equal to 0. Now, now do the calculation. Remaining part. Okay, like this. So limit. Okay, it is output. So at this stage, we need to recall a limit from calculation 1. 0 positive infinity. So if x is positive infinity, then it is 0. If x is negative infinity, then it is positive infinity. So we can write like this. So the fs would be 1 by s. In this case, the domain of the transform is set of the all positive real numbers. So it is a domain of all positive real numbers. Now see table of transforms. It is required that f of t is equal to 1 where t is greater than or equal to 0, and f of s is equal to 1 over s is greater than or equal to 0, f of t is equal to t to the power n where t is greater than or equal to 0, f is equal to like this. Okay, that is the Laplace transform of this. So this is the time domain, this is the frequency domain, s is the frequency domain, t is the time domain. Okay, so t is the time domain, if s is in the frequency domain. The Laplace transform is linear if a is a constant and f and g are functions. Then let's say a is a constant and f and g are functions. So we can write like this. Okay, the equation. These are the property of the Laplace transform. If L of f, where L of f is equal to a into L of f, and L of f plus g is equal to LF plus L of g. So that means it has the property which is the linearity. So it has the linear property. For example, by the above property, L of 3 to t to the power 5 would be 3 L of t, Laplace transform of t to the power 5. Or we can write like this. And see, by property 2, Laplace transform of e to the power 5t plus cos of 3t is equal to Laplace transform of e to the power 5t plus Laplace transform of cos 3t. Just do the job. How we get this? We have to look at the table. Okay, see, e to the power 80, that means 1 over s minus a. Cos means s square plus k square. Okay, s square plus k square. S square, k means 3. 3 square 9, where s is greater than 5. That is the second property. Okay, now let's look an example where both 1 and 2 are used. Where both the examples are used. So Laplace transform of 3 to e to the power 7 plus 8. So we can write like this. So 3 t to the power 7, we can take the Laplace. 3 would be outside, t to the power 7. Now 7 is 8, 7 plus 1, and like this. The Laplace transform of the product of two functions is not equal to fg. Okay. So here is another example, Laplace transform of 3 plus e to the power 60 whole square. So we can write like this and just do the multiplication. Now break all things. Okay, and then see, 9 would come outside, 9 by s, so 6 would be outside, and here, so it is the output. So the respective domains of the above three transform are s to the power 0, it is s to the power s is greater than 0, here s is greater than 0, here s is greater than 6, here s is greater than 12. Equivalently, s is greater than 12. Okay. So that is the example of Laplace transform. Now the inverse Laplace transform. Let f be a function and LF be its Laplace transform. Okay. So then according to the definition, small f is the inverse transform of f. This is denoted by L to the power minus 1 function of f is equal to f. Okay. As an example, from the Laplace transform table, let's say that we have found this from the Laplace transform table. So if I want to find the inverse Laplace transform, then it would be like this. Okay, recall that Laplace transform of t to the power n is equal to this one. Hence, for example, l to the power minus 1, 7, factorial 7 divided by s to the power 7 plus 1, 8 is equal to t to the power 7. Here, by examining the power s to the power 8, we saw that n is equal to 7. Here, n plus 1 is equal to 11, hence n is equal to 10. Now we need to make the numerator to be 10, factorial 10. So here the factorial 10 would be the numerical. Okay. Now, more examples of inverse transform. Consider this one. The form of the denominator s square plus k square is that of the Laplace transform of sine by cos. So we can write like this. Inverse Laplace transform 7s divided by s square plus 2. Inverse Laplace transform 15 divided by s square plus 2. So you can write like this. Take this out, 15 out. Now instead of this, you can write like this. Okay. So it would be the inverse Laplace transform. So partial fractions. Consider the rational expressions 3s plus 5 by s square minus 3s minus 10, 3s plus 5 divided by s minus 5 into s plus 2. The denominator is factored and the degree of the numerator is at least one less that of the denominator. In fact, it is exactly one less than the degree of denominator. Okay, like this. We can therefore put the rational expression in partial fractions. This means the constants a and b. So we can if we decompose it, okay, like the partial fraction, then we'll get these values. By this is the Cramer's rule. Okay, this is the Cramer's rule. Just look at here. Determinant 3 comes here and 5 comes here, and the 1 5 1 minus 5. Okay, 1 minus 5 for the a, you can write like this, and determinant 1 2 1 2 1 minus 5. For the b 3 5, sorry, 1 2 1 2 3 5, and determinant 1 2 1 minus 5, like this. Okay, this is the Cramer's rule. So by the definition of the determinant, we know that AD cross multiplication AD minus CD, BC or CB. Hence A would be 20 by 7 and B would be 1 by 7. And we can now determine the inverse transform, inverse Laplace transform. Okay, we can determine inverse Laplace transform. 3s plus 5 by s minus 5 into s plus 2. So just just break it like this. Okay, bring out the A and B, then C. Okay, like this. This could also have been directly determined by using a formula from your table of Laplace. Okay, so you can find it out from the table also. Okay, which has been given here. So, okay, so this is another example to find out the inverse Laplace transform. Okay, partial fractions. They have given more examples of partial fractions, so I'm not going to that. Okay. Transforms of derivatives. Okay, I will not go to from the first equation. We get that. Okay, this is the solution. Okay, this is the solution. Just if you do the practice, then you would understand. And derivatives transformation, given a function y of yt, the transform of its derivative y prime can be expressed in terms of the Laplace transform of y. L of y prime is equal to, okay, like this. No. Some examples. And say unit function and piecewise functions. So this is a step unit function. Okay, unit function can be used to express piecewise functions. It would be one. It would be 1 when the t is greater than or equal to 0 a, and it would be 0 if the t is range of 0 to a. So let f be the piecewise defined function. So 4 and 6. So now consider the function 4 plus 6 minus 4. 6 minus 4 is equal to u of t minus 8. So when the t range of 0 to 8, then it would be like this. Okay. Another example, another piecewise function. Okay. So truncating a function, see, you can change the function like this, graph. Convolutions, I think, let's say f and g be functions. F and g be functions. The convolution of f and g would, we know that this is the way of writing the convolution. Okay, that is the formula. Thus, in a convolution integral, in general, you will see a tau factor. You will say tau factor is the t in output by f replaced by tau. f is replaced by tau, and t minus tau factor, the t in the output by g replaced by t minus tau. So sine 3t convolution of e to the power 5t would be like this, where tau factor t minus tau factor. Let so see this example, convolution example. F of t is equal to t square and g of t is equal to 2t plus t. Find f in convolution of g. Okay, put the formula, write the formula. Now 0 to t, f of t, instead of f of t, we can write the t square. So instead of t, you write the tau square. And instead of g of t minus tau, we can write 2t. Instead of t, we'll write the t minus tau. Okay, d tau. Now do the job accordingly. You just multiply it, then you'll see 2t plus 3 minus tau. Okay, like this. Just solve it, and the solution is this one. So finally, instead of tau, write the value here, the t. Okay. Now express the following integral as a convolution. Now you have to say, they asked you to express the expression into the integration form. So tau factor, replace tau by t to get the first factor of the convolution, replace t minus tau by t to get the second factor of the convolution. Okay, like this. Now another example. Example 4 or 5. Some examples are there, you can see. So Laplace transform of convolutions. The Laplace transform of the convolution product of two functions is not equal to the product of the two transforms. Okay, so these are not equal, but the convolution will be equal. Convolution of f from g is equal to Laplace transform of f and Laplace transform of g. Without evaluating the integral, find this one. So by example 3 of the previous slide, say like this, we can write like this. Here is another example. Okay, the effect of multiplying this input to the Laplace transform by e to the power t is to replace the s in the output by s minus 1, and it is the equation. It would be the equation here. And Laplace transform of 0 to t, integration of 0 to t, t sine of tau d tau, where you can do this one. Okay, just replace this. And some examples are also there, and integral differential equations are also there. They have given. Okay, some equations are there, lots of equations are there, so you can check by yourself. And other the Direct delta function, a direct delta function. Okay, delta equation, Laplace transform. Okay, some systems of equations like x of x is equal to x of t is equal to y equal to of t b function of t. Suppose x prime, this one. Okay, and Kramer's rule, they have used the Kramer's rule here. And periodic functions are also there. The part is repeated. Okay, the periodic function. Okay, find the Laplace transform of the periodic function f whose graph is given below. Okay, like this. Some examples are also there. Okay, so here it is, this chapter. So I have not touched all things. So you have to see which parts I have shown. So you just check this out. Okay.